That was super fun to start our shaking things up, earthquake preparedness and resiliency, August Midday Science Cafe with a little bit of Taylor Swift shaking it up herself. So, hello everyone. Thank you so much for joining our Midday Science Cafe this August. We are so excited to have you here for Shaking Things Up, Earthquake Preparedness and Resiliency with Dr. Floriana Petrone from Berkeley Lab and University of Nevada, Reno, and Dr. Sarina Patel from UC Berkeley Seismology Lab. Just a few things before we get started. You can find closed captioning for the Midday Science Cafe in Zoom. Either it popped up automatically or it's in the three dots under More, but feel free to open those up and follow us in text. This is being recorded and we'll post this video to the Science at Cal YouTube channel and the Berkeley Lab YouTube channel, and we'll share that link with you all via email once it's posted. My name is Michelle Rodriguez, and I'm so happy to be with you all today. I am Science at Cal's interim public engagement specialist, while our executive director, Dee, who you normally see on this screen, is out on maternity leave. If you didn't hear last month's Midday Science Cafe, she had twins. As we normally do with our Midday Science Cafes, we are going to start today with a land acknowledgement. We recognize that Berkeley sits on the Huchun territory, the ancestral and unceded land of the Ohlone people, the successors of the historic and sovereign Verona Band of Alameda County. This land was and continues to be of great importance to the Ohlone tribe and other familial descendants of the Verona Band. Every member of the Berkeley community has and continues to benefit from the use and occupation of this land since the institution's founding in 1868. By offering this land acknowledgement, the Berkeley community not only recognizes the history of the land on which we stand, but also recognizes that the Ohlone people are alive and flourishing members of the Berkeley and broader Bay Area communities today. Thank you for allowing me this time to give this land acknowledgement. In 2008, Science at Cal was envisioned as a unifying effort to raise public awareness, understanding, and appreciation of scientific research at Berkeley. To realize this vision, we engaged the vast Berkeley science, technology, engineering, and mathematics community to foster creative collaborations among campus and community-based groups who share our commitment to equity and inclusion in STEM education and careers. Science at Cal connects researchers with diverse community groups of all ages and backgrounds for science engagement and learning. Accessibility, inclusiveness, creativity, and innovation are all hallmarks of Science at Cal events, which reach tens of thousands of people annually. Throughout the year, Science at Cal presents ongoing free outreach programs on and off campus, helps promote related efforts, and creates new programs and initiatives at Berkeley and in the community. This broad scope of activities is made possible by Science at Cal's dynamic network of campus alliances and valuable community partnerships. Before I hand things over to Berkeley Lab to say hello, I want to remind you that these events are always really interactive. So we expect a lot of Q&A, so please add your questions into the chat or the Q&A box. You don't need to put them in both, and we'll get to as many questions as we can. And now I'm going to hand things over to Jen Ting with Berkeley Lab.
Awesome. Thanks so much, Michelle. So hello, everyone. For those who don't know me, I'm the Director of Community Relations at Lawrence Berkeley National Laboratory. And those who might be joining us for the first time might want to know that Berkeley Lab is one of 17 U.S. Department of Energy national laboratories across the country. We are supported by the DOE's Office of Science, and we're managed by the University of California. All of the research we conduct at the lab is unclassified. And since our founding in 1931 by a UC Berkeley physics professor named Ernest Orlando Lawrence, we've been dedicated to advancing the scope of human knowledge and seeking answers to some of the greatest problems facing humankind. Today, Berkeley Lab employees work together to develop meaningful scientific solutions to the world's most intractable energy and environmental challenges. They help train the next generation of scientists and engineers, and we ensure that those things happen in a manner that benefits everyone. Our main campus is located in the Berkeley Hills, and our close ties to the UC system create a really unique and synergistic environment for scientific discovery. A number of the lab's researchers are affiliated with one of the UC campuses, either as students, postdocs, or professors who might have a joint appointment to do research at the lab. And we're fortunate to have an especially close relationship with UC Berkeley, and our institutions have joined forces to advance science across many different frontiers. One of the main motivations for creating the Midday Science Cafe series is to share with you examples of compelling and complementary scientific research from both of our institutions. And we hope that you enjoy today's presentation about earthquakes. So with that, let me hand things back over to Michelle to introduce our first speaker.
Thanks, Jen. So I have the pleasure of introducing Sarina Patel. She is a fresh off the press PhD grad, congratulations, from the UC Berkeley Seismology Lab. Her dissertation focused on the MyShake app, which is both a citizen science project to collect seismic data for research and is a delivery service for earthquake early warning in California, Oregon, and Washington. Sarina also helped teach a course called Earthquakes in Your Backyard, which aims to equip non-science majors with fundamental knowledge about earthquake processes and how to be prepared to survive and thrive in earthquake country. She enjoys engaging the broader community in earthquake education, be it in public talks like this one, or at the libraries, or in elementary school classrooms. In November, she'll be starting a fellowship in science policy in Sacramento, and in her spare time, she loves to read, hike, and sew. It is my absolute pleasure to introduce Sarina, and Sarina, the floor is yours.
Thank you so much. So today, I wanted to give a bit of an overview of some of the things that I did in my research during my PhD, and all of this focuses on a project called MyShake. So MyShake is a free citizen science smartphone application. It was developed by a former graduate student in my lab named Chin-Kai Kong and launched publicly in 2016. Since then, it's been downloaded globally more than 2.5 million times. So that's all of the green points on this map. And today, it is an independent project operated out of the Berkeley Seismology Lab by a team of developers and project managers. So in our quest to be a bit of an earthquake ecosystem for our users, we have a number of features, including this one, earthquake information. So all of these orange points are earthquakes, and you can click on them to learn more. We have safety and preparedness information based on the 7 steps to earthquake safety. We also have community source damage maps. So if you experience something, you can click that green button and fill out a quick picture-based survey. And we aggregate these community feedbacks into maps so that other people who are using the app can get a quick picture of what's going on after an earthquake. And critically, as was mentioned, we are the official delivery service for earthquake early warning in the states of California, Oregon, and Washington. Of course, the other significant core of MyShake is that it's a citizen science project. And this is based on the fact that all smartphones have a sensor in them called an accelerometer. An accelerometer is the thing that when you turn your phone from upright to sideways, it changes the pixel orientation, but it's also a vibration sensor. So we try to use that to measure earthquakes. So when someone has MyShake on their phone, but they're not using their phone, so the phone is sat quietly on the table for at least 30 minutes, we will start monitoring those vibrations to see if we can find earthquakes. And the reason why we can do that is because of a fundamental observation that Chin-Kai made about the nature of earthquake motion, which is that most of the motions experienced by a phone related to human activity, like going for a run or being in a car, are physically different than the vibrations caused by earthquakes. So all of the red points in this chart are the earthquakes, and the blue are people-related motions. And you can see that they occupy 2 different parts of the chart. And that means that Chin-Kai was successfully able to create an algorithm that could tell the difference. So if we're watching the accelerometer and we see an earthquake, we'll record for 5 minutes and send that data back to our computers. And that formed the backbone of the data that I used for my dissertation. So this launched in 2016. I arrived in 2017. So we were collecting this information, but what we didn't know yet was what phone data was capable of. So I just tried a bunch of different things to see what would happen. So one of the things we wanted to look at was, if we're going to be a delivery service for early warning, how well are we doing? Another was, if we're doing these earthquake detections, could we contribute to the generation of early warnings in the first place? I'm not going to talk about that today, but I'm happy to take questions about it. And the third thing was more of an engineering application. So if we're recording earthquakes, but usually if you put your phone down and you're not using it, you're inside, that means that not only are we capturing how the ground is moving, we also might be capturing how the buildings are moving in response to that ground motion. So I'm going to start with earthquake early warning. Earthquake early warning is a project in the US called Shake Alert. It's operated by the United States Geologic Survey in concert with a number of universities, including Berkeley. And it's built on an infrastructure backbone of a bunch of seismic sensors that have been installed across the landscape. That's represented here by all the little cylinders. And they're constantly streaming vibration data back to the central computers. So let's say we have an earthquake. A fault ruptures and releases a bunch of energy. This energy radiates away from the fault in the form of seismic waves. The fastest of these is the primary, or the P wave, and it's followed on behind by the secondary, or S wave. The P wave is the least strong of all the seismic waves. So if you're going to feel shaking in an earthquake, it's generally going to start with the S wave. And if there's going to be damage from an earthquake, it will also usually start with the S wave. So early warning takes advantage of this fundamental difference, the fact that the fastest wave is also the least destructive. So what we want to do is pick up on those P waves, detect that the earthquake has started, and send little snippets of data very quickly to a computer running a series of algorithms, which can then backtrack where the earthquake started and how big it is, so that it can then forward project who it's going to affect, so that we can send people and systems alerts so that they can take action before the S wave and the shaking arrives at their location. So early warning is fundamentally a race between technology and earthquake waves. And technology is good enough now that we could actually win that race. So this last leap between generating an alert and getting it to people, that's what MyShake does as a delivery service, sending alerts to individual smartphones. So when the project started, it was always the goal to be able to do this. We wanted to send alerts to the public at large. And we had a goal of doing this within 5 seconds. But what we didn't know was whether that was actually technically possible. So MyShake requests receipts to make sure that phones actually received alerts. And we use that to then measure how quickly we were able to do that. So the horizontal line in this chart, that's the 5-second goal we wanted to meet. And you can see the first 2 events on the left are above that line. We're not quite making our goal. So the MyShake team implemented something called parallelizing or sharding. This is where you ask, instead of 1 computer to do a computation, you split it up amongst 3 computers or 6 computers, and now we have 12 computers doing this in parallel to make it faster. And you can see that the result is most of the points now after that process have dropped beneath the 5-second line. So consistently, even as our network has grown and as the earthquakes change size and we have to alert different numbers of people, we are consistently meeting our goal of delivering alerts within 5 seconds of the alerts being created. So this is great. We had this fairly ambitious technological goal and we've managed to achieve it. However, that's from our perspective in terms of our technical capability. Early warning fundamentally matters whether or not those alerts will be useful. So this is another way of looking at that. The question that we ask with these charts is how many people received an alert before shaking or the S wave would have arrived at their location. And I'm using an example of the San Jose earthquake that happened last year. And what we want is for as many points as possible in these charts to be green. And that's where the warning time was positive. And this is one of the more challenging alert cases that we're going to have to deal with. This is where the earthquake is right underneath a portion of the population that we're trying to alert. And that means that we're never going to get 100% green because some people are ultimately going to be closer to the earthquake than even the sensors we're using to detect it. However, even in this super challenging case, 66% of people received an alert before we expect the S wave arrived at their location. So that's an exciting thing to say about a really challenging use case. A larger earthquake that happened in the far reaches of Northern California gives us the other end number. So in this earthquake, the people inside the dotted black circle were too close to the earthquake to receive an alert before they would have felt shaking. However, down here in the Bay Area, there was up to 90 seconds of warning. And for the shaking that was experienced in that earthquake, that wasn't necessarily like the biggest deal, but the 1906 really famous earthquake ruptured from where this star is all the way down to the Bay Area. So now imagine if you'd had 90 seconds of warning to take scalpels out of patients and stop elevators at floors before the 1906 earthquake happened again. So this is the real power of being able to measure and set expectations for what we might be able to do with early warning. Okay, now I'm going to take a hard left turn and talk about an engineering application. So structural health monitoring is the engineering field of assessing how structures respond to forces. In this case, how buildings respond to earthquakes. And we can model this until we're blue in the face. We can make extremely sophisticated mathematical expectations of how structures should behave when certain things are applied to them. But it's a lot harder and rarer to have actually measured this in real structures, primarily because it's resource intensive. It's costly in terms of time and resources to put all these instruments in buildings and collect the data and make sure those networks are maintained. So that means that we have a gap now between our expectations of how buildings are going to respond and actually having gotten to see that in the complicatedness of reality. MyShake is a really interesting opportunity in this space because people are naturally, with MyShake on their phones, occupying buildings. So we have the possibility of being able to make these measurements while skipping a lot of the overhead that makes it a challenge in the first place. So with that opportunity, we have two starting questions. The first is, are phones good enough to record interesting things about buildings? And the short answer to that is yes, and we're very excited about it. So that being true, what interesting things do we want to know about buildings? And I'm going to start with something called fundamental frequency. Fundamental frequency is something that is inherent to all solid rigid objects. And I can use the example of a tuning fork, which is a rigid object that was specifically designed to have a fundamental frequency. So if you tap a tuning fork, it will vibrate, basically wobble back and forth, and that will shake the air and register in the human ear as a music note. Buildings will do the same thing. If you shake them with an earthquake, they'll wobble back and forth at a fixed rate. That's due to the structure that it's made of. And if you damage the building, if you shake it hard enough, you will actually cause that rate at which it sways to reduce, so the frequency will lower. So we can use fundamental frequency basically as a diagnostic of potential damage. Another thing that's really useful as a starting point for this kind of work is that fundamental frequency is inherent to the entire structure. And that means that as we get a start, we don't need to worry about where in a building a phone is located, or if we have multiple phones. One measurement anywhere in a structure can net us this value. So here's an example of us actually doing that. There was a hotel, and someone was inside this hotel during a small earthquake, and we were able to capture that earthquake on their phone. So that's the black squiggle in the top panel. And you can see there's the main body of the earthquake, which is the big and tight squiggles. And then the earthquake is mostly over, and what takes over in the vibration is actually the swaying of the building, the resonance that gets left behind. So I'm going to take this part that's highlighted in turquoise and actually look at the rate at which those sways are happening. That's called the frequency domain. And what we want to see is one really distinct point, and we see that at about 2 hertz. And that's a completely appropriate value for a structure of this size and dimension. So that's cool. We have a few examples of this where we've measured earthquakes and then taken the resonance at the end of the earthquake, and we're actually able to see something about the building in which the phone was located. Now, the next step, of course, is we want to be able to detect damage if something happened. This is a small earthquake, we expect no damage, but what if something big happened? So we did an experiment. This is a shake table facility. This is a 3-story structure that's built on top of a hydraulic table that can move in 3 dimensions and mimic earthquake motion. And this 3-story structure is built with an experimental technology called a tension rod, and I've circled one of them in green. The notion is that if you apply motion in the direction parallel to these rods, so the red arrows, the tension rods will absorb some of that energy by basically replicating what in a normal building would look like softening or breakage, except that when the earthquake is over, the tension will actually go back to the original stiffness, so the building will resume its normal behavior. So what we're going to see in the frequency space is when the tension rods engage, the frequency will drop. So let's look at that. Here we replayed an earthquake that happened in Turkey 3 times, and that's the top part with the black squiggles. And then I've also put it into what the frequency looked like over that same period of time. And what we wanted to see was bright horizontal lines indicating the resonance of the building getting excited by the vibrations. And we do see that. We have a fundamental frequency here. We even have a secondary and a possible tertiary one boxed up in white here. So now let's talk about what it might have looked like to diagnose damage happening in the building in real time. So I'm going to focus on just the first earthquake, and we're going to look at before, during, and after. And this is that in the frequency space. And I'm going to focus on just the fundamental frequency, which is the lowest frequency part here. And we're going to zoom in on it, right? So before the earthquake, which is the blue line, we expect the full stiffness of the building to be in place. So we're measuring the fundamental frequency of the building in its healthy state. And then during the earthquake, that's going to drop because the tension rods have engaged. And then what we want to see is it go back after the earthquake is over because the stiffness has resumed. What we actually don't see is it fully recovering. And what we learned was this was because some of the bolts on the structure had loosened, and therefore it was not fully able to regain its original stiffness. So this is a really remarkable validation of the degree of detail that we could get using phone sensors, even though they're not as high quality as the things that we normally spend a lot of money on. So this gives us a lot of hope that we can, with a pretty good amount of detail, actually see changes in stiffness and therefore fundamental frequency in buildings, and potentially be diagnosing damage without even visiting those buildings because we're using our users' phones. So this feeds into a grand vision that we have, and that is to form a long-term monitoring network of the buildings where MyShake users live and work. And we'll leverage small impulses like an earthquake to record healthy behavior as a baseline when no damage is expected. And then when we have a really significant earthquake, when, not if, unfortunately, we can look for the new resonance, maybe in the tail of the big earthquake or in an aftershock, and compare the two. And if damage had occurred in that structure, we would expect the fundamental frequency we measure after to be lower than the one we measured before. And this remote diagnostic would be something that we could then feed to the engineering teams on the ground who have to go around and survey all buildings after a major earthquake and give them a heads up, like, hey, you might want to prioritize these sets of buildings where we have seen indicators of potential damage, or you might want to go and open up the walls to make sure the internal structure is okay. And this will really help because after major earthquakes, the resources are always limited. There's never going to be enough engineers to get everything done in the time that we want. And so tools like this, MyShake is really excited to be able to contribute to the recovery process by feeding this kind of information to help people make decisions. And I'll stop there, and I'm super happy to take questions.
Sarina, thank you. That was awesome. The MyShake app sounds like such a powerful tool for both warning us about what might be coming our way, but also to help earthquake safety after the fact. That's really exciting. I have a question about the health of monitoring the buildings. You've done tests.
Mm-hmm.
What would that look like, or what could that look like on a larger scale? Like knowing, once we worked out all of the kinks and, that it works, what would that look like to be able to like monitor every building and
Mm-hmm.
like what happens then?
I mean, basically, we want to build a really big database. So there are free databases of using satellite data that has basically created a catalog of the buildings that exist. And so we would then use that as a starting point, and every time we make a measurement in one of those buildings, we would associate it with that structure. And this means that now we have a time history of what that building normally does when something significant hasn't happened yet. And then when something does happen and we make measurements in it later, now we have this history and we just compare the new value to it. And because we already know something about those buildings, now we have basically a geotagged catalog, a map. And you can just flag the buildings on that map where you've made a measurement and you're worried about it, and then hand that over to the engineering powers that be.
That's so neat. We have a question that just came in related. We have a couple of other questions too, but this one just came in related to what we're just talking about. So this person's very interested in the damage assessments, and as an emergency planner, currently working on post-earthquake damage assessment program. Is there anything that we can do or technology that we can buy into now that will assist us post-earthquake with respect to damage assessments?
I mean, there's definitely a burgeoning market of basically low-cost internet-based sensors where they look like this, that like the size of a deck of cards. One of the companies is Raspberry Pi, Raspberry Shake, which is built on a Raspberry Pi little computer. And basically you can plug those in and connect them to Wi-Fi, and they'll stream data back to whatever sort of home base you give it. So if you're able to do that kind of thing in, for example, public buildings where you might have that kind of access, then you could basically start doing the type of work that MyShake is doing, and using this as a long-term monitoring network to try and extract some of these features. And then the other types of things are, like improving the robustness of the databases that we work with about the building. So like I work with a database called OSM Buildings, which is a public database, but not every piece of data in it is correct. And so anything that can feed into making that like more robust will also help. So those are like the types of things that you can do. And then also just building relationships with the people who are doing work like this, like the Pacific Earthquake Engineering Institute, or the California Geologic Survey has a strong motion program where they've actually gone and instrumented buildings and they're monitoring them long term. So that kind of partnership also would help.
That's great. So it sounds like partnerships, and there are technologies out there, but also we should all download the MyShake app so that we can
also please download the MyShake app.
There's another question that just came in about, are you keeping the servers on which MyShake connects remote from the earthquake prone zone? If not, what's the risk that it will become unavailable in case of an earthquake?
So we do, I think we have redundancy on our servers, and certainly earthquake early warning does. So they have servers up and down the West Coast. So if something happens in Southern California, the computers in Northern California and Seattle can keep going. And so something like that would sort of be the same idea with MyShake, is just not necessarily keeping all of our resources where we expect the earthquake to happen. But the other challenge, which we anticipate, and it's just really hard for us to solve, is connectivity, right? So if the cell phone towers become overloaded, or if people just don't have Wi-Fi for a while, right, like it's just going to be harder for us to collect data, but it's also just going to be harder for all forms of communication to happen. And so that's much a bigger infrastructure level problem solving thing, is how are we going to stay connected to both, generate and send data, but also to communicate as emergency response people to organize the relief effort. And so basically whatever innovations happen in that space, MyShake will be piggybacking on.
Oh, that's great. We'll pivot just a second to on the user side of MyShake. And there were a couple of questions about the advance warning and how much advance warning there is. And also, so I think I remember you saying that 5 seconds was like this, the goal, the ultimate goal. And so what, how one is, what can we do in the 5 seconds? And then also, how does MyShake warn the public or any specific user to take cover? What is the actual warning?
Yeah.
And then we'll turn this over to our next speaker. I'm sorry, I'm just kidding.
No, that's good.
Too much.
So I should clarify, the 5 seconds is how long it takes for us to get the alert onto someone's phone.
Oh, got it. Okay.
So Shake Alert produces the alert, and then within 5 seconds of the alert being created, we've delivered it to phones. And then the amount of time that you're going to have before the shaking arrives is going to depend on how close you are to the epicenter. So that's like basically shown by, we'll go back really quick. This map. So all of the green circles are marked with this timestamp. That's how much time we expect that person within this circle to have before the shaking arrived at their location. So someone, at this far away from the earthquake had 5 seconds, but someone much further away had about a minute. So it's going to be completely dependent on how close you are to the epicenter. So, the amount of time that it takes the S wave to arrive at your location minus the 5 seconds it took us to get that alert to you. And then the alert itself is what's called a critical notification. So it is something that can go through your silent and do not disturb. And we only do that if the earthquake is at least a magnitude 4.5, and we expect that you are going to feel weak shaking or stronger. So like when you would actually want to know about the earthquake, as opposed to just like anytime an earthquake happens anywhere. And it's a pop-up, so there'll be an alert. If you click on it, it'll take over your whole screen with a drop, cover, and hold on triptych. And it's basically a picture diagram giving you instructions about what you should do to make yourself safe. And it's specifically if you're like what I'm doing right now, I'm sat at the desk, then I would know to drop what I'm doing and go under the table and take cover. There also are behaviors that you can find on the 7 Steps to Earthquake Safety website about what you can do in other situations, like if you're driving, if you're in a wheelchair, if you're outside. There's instructions that you can find to sort of prepare yourself for all the different situations you could be in if you receive one of these alerts.
Cool. Thank you. Thank you so much. We'll go back to, there's more Q&A after our second talks. I'm going to turn things over to Jen to introduce our next speaker. Thanks, Jen. Thanks,
Awesome.
Sarina.
Yeah, thanks so much, Sarina, for that great presentation. It is actually now my pleasure to introduce our second speaker, Dr. Floriana Petrone. So Floriana is an assistant professor in earthquake and structural engineering at the University of Nevada, Reno, and she's also a visiting faculty scientist in Berkeley Lab's Energy Geosciences division. Prior to her current roles, Floriana worked at Berkeley Lab as a postdoc scholar and a research scientist focused on the development of advanced numerical tools for the seismic nonlinear analysis of the U.S. Department of Energy nuclear facilities and systems. Her current activities at UNR and Berkeley Lab include the study of site-specific variation of earthquake structural risk at the regional scale for buildings and distributed systems. She also looks at the investigation of new techniques for structural damage prediction through advanced numerical analyses and machine learning, and the development of the new generation data-informed infrastructure seismic risk models. In her spare time, Floriana is an avid reader and she likes to go hiking. So Floriana, I'm going to turn things over to you.
Thank you so much, Jen. It's a pleasure to be with you all today. And I'm here to talk about some recent advancements of a project supported by the US Department of Energy exascale computing project, which involves scientists and faculty from different institutions, including Berkeley Lab, Lawrence Livermore National Lab, and University of Nevada, Reno. My talk is entitled Charting New Frontiers in Earthquake Science and Engineering with Exascale Computing. And it's going to provide an overview about how exascale computers, which are the most powerful computers in the world at the moment, can be utilized to enhance our understanding of major earthquake and improve the resilience of infrastructures. Now, just to give some background, so the DOE Exascale Computing Project aims at developing the application software and integration codes needed to exploit the immense computing power of exascale machines, to advancing knowledge across diverse fields, from energy production to material science and natural hazards. So the core concept is to utilize modeling and simulation to study phenomena and systems that otherwise would be impractical, if not impossible, to investigate in the real world, given their complexity, their cost, and their size. And so major earthquakes and civil infrastructure fall exactly in this category. So in this context, the earthquake simulation application, which is also called the EQSIM, which is developed under the umbrella of the Exascale Computing Project, aims at creating a computational toolset and workflow to perform earthquake simulations to get prepared for earthquakes and their consequences. Now, but let's see how the overarching goal of EQSIM really relates to the exascale challenge. So in other words, why do we need supercomputers to perform earthquake simulations? So the final goal of the EQSIM application is to enable the simulation of earthquakes physics from the initiation of the fault rupture to surface ground motions, to finally assess the infrastructure integrity at the regional scale. And when we talk about infrastructure at the regional scale, we really refer to a broad range of structures, from pipelines to long-span bridges, buildings, steel, nuclear power plants. And if we think about it, the capability of withstand major earthquakes of all these structures is tightly tied to the wellness and resiliency of modern society. And so as a result, we would like to be able to fully understand how all these systems are going to respond to a major earthquake. However, if we look at the x-axis of this chart, we will see that as we go towards more massive structures, so stiffer structures, we see that they are characterized by higher frequencies. So the same concept that Sarina was explaining. And computationally speaking, if we want to simulate ground motions that can resolve these high frequencies, this means that we need to perform our computations on models that have billions of grid points. And this really makes the goal of this application very ambitious and poses the challenge of being able to run much larger models much faster, since we want to be able to execute analysis at frequencies that are important for our infrastructure systems on extended urbanized areas with realistic geology. And also, we would like to be able to run many of these simulations to account for all the uncertainties of at least most of them that are associated with natural phenomena. So let's see how EQSIM is actually responding to this challenge. So here on the left, you see a typical simulation model that is utilized and is developed within EQSIM. It's really like a volume of Earth, which incorporates the geology, the topography, and also representation of the fault. Now, within EQSIM, with SW4, which is another application that is part of EQSIM, we are able to simulate the rupture of this fault along this plane here, and then the propagation of the waves across the entire domain. And as a result, we're able to study the response and the behavior of all these structures that ideally sit on this domain. So clearly, this is a pretty intricate physics-based model that counts billions of grid points. So in order to solve this model, we need to just utilize advanced supercomputers. So here on the right, I'm showing a plot where on the x-axis, you will see the years. And then on the y-axis, the computational power expressed as a function of flops. And so if you follow these red dots here, you will see that there's been a pretty nice and steady just increase in the computational power over the years. Till today, where the most powerful computer in the world is Frontier, which is hosted at the Oak Ridge National Lab and is the computer that we are actually utilizing for performing these simulations. Now, it's pretty clear that to go from a geophysics model to structural responses, infrastructure responses, there are quite a few steps we need to take. And so here is a presentation of the EQSIM workflow. So really, we start from the selection of a region and a fault we're interested in, and we build a geophysics domain. So then we generate gram motions on billions of nodes, and then we analyze this gram motion. So this is a very important step, this one here in the middle, because really we're utilizing very sophisticated models on these just very powerful machines. But at the end, before moving to the analysis of the structures, we want to make sure that these gram motions are realistic. And so what we do, we look at multiple characteristics of these motions, and we compare such characteristics with real records from all over the world and with empirical models. And what I'm showing here in this plot is one of these comparisons. Now, once we have gained confidence in the utilization of these motions in engineering domain, we select a structure. We ideally place this structure across the domain, and then we start studying analyzing the behavior of this structure in response to the gram motions. And then as a result, we can generate maps that show, for example, the distribution of the damage, the demand, or just potential displacements. And so there are really just a lot we can do with this data. So clearly, so by nature, this project is a just multidisciplinary project. And as a result, also the team working on this project is highly multidisciplinary, with people having a background in engineering mechanics, seismology and geophysics, computer science, very important, as well as applied math and numerical methods. And of course, the whole project also relies on a lot of great work done by postdoctoral scholars and graduate students. Now, so far, the EQSIM application has focused on the San Francisco Bay Area, and in particular on the simulation of earthquakes generated on the Hayward Fault. But why the Hayward Fault? So it's not just because it's the fault sitting right in between Berkeley Lab and UC Berkeley, but as we all know, research has demonstrated that the Hayward Fault has now a 31.7 chance of rupturing in a 6.7 magnitude earthquake or even larger before 2036. And if this is not convincing enough, so here on the right, I'm showing a timeline of strong records where each star indicates a different earthquake, major earthquake. And so if we look at these colored numbers here, we will see that the average time interval between earthquakes is about 150 years. Well, if we think that the last largest event on the Hayward Fault was in 1868, well, that means that it's been 155 years ago. And so a major earthquake on the Hayward Fault is now expected at any time. In addition to this, the Hayward Fault is located in a highly urbanized area with more than 2.4 million of people. So if a major earthquake is going to strike this area, this is going to have a huge impact on society, on the wellness and economy, not only at the just local level, but also at a more global level. So with our just simulation models, we're really able to generate a large amount of data. They really just are invaluable for the earthquake research community and engineers, particularly those who are just interested and seek to build just a retrofit earthquake resilient homes, businesses, and infrastructure. And really with this amount of data, there are just a lot of analysis we can conduct. So today I'm going to show just a couple of examples of what we can do with this data. And so the first example is about one single building we might be interested in, located at a specific site in the San Francisco Bay Area. So the building is the one shown here on the right. It's a tall building, and the location in the Bay Area is represented by this red dot. On the left, you see the seismic waves propagating just away from the hypocenter here indicated with this yellow star. And concurrently, you see also the deformation and the displacement of the building. So on the building, wherever you see green, that means that that portion of the building has not really experienced any damage. Whereas when you see yellow and potentially orange and red, that means that the structure has experienced an increasing damage. So this is, again, just one example, but then what we can do, we can extend this type of analysis to the entire domain and then obtain what we call the building's damage distribution at the regional scale. So now on the left, I'm showing an animation of a simulation of a magnitude 7 Hayward Fault event with the hypocenter located on the southern side of the Hayward Fault. And on the right, I'm showing the evolution of a damage for a representative 12-story building located in the San Francisco Bay Area. And you can see that as the waves propagate across the domain, the structure are shaken and just experience damage. So on the left here, whenever you see a color that is towards red, that means that the shaking, that indicates a stronger shaking. Whereas whenever you see like these colors towards blue, that means that the shaking is weaker. So it's not usually not damaging to the structure, but can still be felt by people. On the right here, whenever you see green, that's good news because that means that your structure has not experienced any damage. But as we go towards yellow, orange, and red, that means that the structure has experienced large deformations. And as expected, for example, here we see that we have a concentration of the damage in the vicinity of the fault. But also you can see that it's not really trivial to understand how the damage changes just across the region. And so you can clearly see that we have spots, we have sites pretty far from the fault where the structures do experience damage, large damage. Now, this was an example of a simulation where the fault ruptures starting on the southern end of the fault. But we don't really know where the Hayward Fault is going to rupture. And so what if the Hayward Fault ruptures starting from the northern side? So here is another animation of the same type. On the left, you will see the earthquake starting this time for the northern side of the fault, with the waves propagating first, just of course, across the fault rupture and then away from the rupture, and so throughout the entire domain. And concurrently, you will see on this plot here on the right, the spread and evolution of damage for the same 12-story building. Now, something interesting to notice here on the left is that it takes about 20 seconds for the full fault to rupture. However, the waves that propagate away from the fault shake the Bay Area for much longer than 20 seconds. And we go above 90 seconds. And this shaking tends to be longer and to be stronger as a function of two main elements. So one is the slip on the fault, and the other one is the local geology. In particular, we know that wherever we have just a softer soil, we tend to see a stronger shaking. So now look at these three areas. Here we have the Pleasanton-Livermore Valley, the San Leandro Valley, and then the Santa Clara Valley. These are just three areas in our domain where the shaking is just very long compared to the remaining Bay Area, and also with a shaking that is pretty strong. Now, let's look at the building response. So in addition to observing, as expected, that the damage is concentrated in the vicinity of the fault, we also have just pretty important and spread damage in areas as the Pleasanton-Livermore Valley here, where we have this strong shaking that just lasts longer for a longer time. So this type of insight is really something that we can obtain only from these high-resolution simulations. And the idea is that we don't really want to stop here. So given that we don't really know, for example, as we mentioned, where the rupture is going to, the fault is going to rupture. So we need to really, the idea is really to run multiple simulations to span the possible range of earthquakes that we expect. And so this will be done, is actually, it's being done by changing the characteristics of the fault rupture and including the location of the epicenter, and also by exploring multiple geologic characterizations. So the idea is that we won't have just 1 ground motion for each location in the Bay Area, but we're going to have just a distribution, so statistics on the expected level of shaking at a specific site. And as a result, we're not going to have just one structural response, but a distribution of the expected structural response at that specific site. And so in this context, what's ahead? So what's ahead is really what is needed for a full transition of ground motion simulations from being a pure research topic to something that can be just utilized and implemented in practice to enhance infrastructure resiliency. And really, there is a lot of exciting work to do, but I would say that there are like 3 main points and 3 main tasks to address on which the EQC team is already working. So the first is the generation and dissemination of suites of ground motions, simulated ground motions, to augment the current databases of records, in particular records at short distance from large magnitude events. And there is currently a collaboration with the Pacific Earthquake Engineering Research Center to share with the community a database of simulated records in addition to the existing database of real records. Second, we want to go beyond the Hayward fault. And so we want to start looking at other faults, as for example, the Sant Andreas faults. And I'm really happy to share with you this screenshot of a very recent simulation that was executed by the same team, showing the same type of animation, but this time of a magnitude 7.5 earthquake on the Sant Andreas fault. And as you can see, in a much larger domain. And finally, what we want to do, we want to be able to start implementing all these research findings and insight into current codes and standards, with the idea that we really want to define a path forward based on the collaboration between earthquake science and engineering with the aid of simulations to really just improve infrastructure resiliency. And so I will stop here, and I'll be just very happy to take any questions.
Wonderful. Thanks so much, Floriana. That was a fascinating presentation. So we've got a couple questions, and stemming off that last sort of bullet point you've got on this slide, thinking about the transition from research to practice, how do you expect the use of simulated motions is going to impact current building design and building assessment?
That's a great question. And a great question for a structural engineer. So let me start by saying that just so far, just most of the knowledge about earthquakes and corresponding structural response has been based on empirical records. And so everything just we do, and that is currently part of the codes and standards for buildings and bridges, is really just based on the knowledge, good knowledge, but fairly limited of the coming from the real records, particularly when we look at major events at short distance. Now, my point of view, and also my hope, is that the findings from these ground motion simulations are going really just to become shortly part of the just current provisions. And there is something we can think about this, making a parallel, just thought, process with these structures. So now we use codes for just modeling structures, and we're all confident in the results we obtain. So moving forward, I think that we are going to build the same confidence. We want to build the same confidence in the use of these tools for simulating ground motions. And the good news is that current codes already contain part of this. So the AC7 2022, and which is the code currently utilized for the design of buildings in the United States, at some point just mentions that if the designer doesn't have enough records to support the design of a structure, can utilize simulated ground motions. So I think, just in conclusion, that really just this is going to just provide an impact, to just have an impact on the design. And the good news is that the community of structural engineers is ready to just receive this, and it's already partially incorporated this in the current standards.
Got it. Thanks for that. So, it looks like you're using supercomputers to build these models. Can you provide a few examples of how long it takes to execute these runs on those supercomputers?
Sure. So, okay, let me put a little bit of background. So in general, really just the time that the computational power and the time that it takes is really just a function of, well, the size of the domain, of course, and then two important parameters. So the frequency resolution we have mentioned, and the site conditions. So what we call the VS min, which would be say minimum shear wave velocity. So meaning if we have just softer soil. And so really just the computational time will be just a function of these two parameters. However, I'll be happy to provide some more details. So just to give a sense of how long it takes on these large, big machines to run these large models. Excuse me. So, for example, on the supercomputers that have evolved over time. So, for example, on Perlmutter, one realization, one of these simulations with a frequency resolution of 5 Hertz with a VSM of 250 meters per second, this will take 9 hours. However, if we go just with we increase the frequency resolution to 10 Hertz, so from 5 to 10, and then we reduce the minimum shear wave velocity from 250 to 140, this will just bring the wall clock time to 42 hours. So this provides a sense of, what is the time that it takes to run a full simulation. We're talking about the generation of the ground motions only. So then we have to add time here when we want to analyze, for example, the buildings. And of course, as we go just higher with the frequencies, and you can see just lower with the velocity, the time will increase on the same machine.
Wow, that's fascinating. Thanks so much for those answers to those questions. And what I'd like to do now is I'll ask you to stop sharing your screen, and I'm going to invite Michelle and Sarina back to the virtual stage so we can start our Q&A. And I think, Michelle, thank you so much. We're going to ask some of the questions.
Awesome. We're going to pivot a little bit into just earthquake science in general. There are a couple questions that are coming in about earthquake patterns. So one is there any clear pattern of an earthquake for comparative study to avoid any false prediction of earthquakes coming? Can you predict an earthquake?
Sarina, you want to go first?
I can take that, yeah. So we cannot predict earthquakes. Basically, what we can do is take the history of earthquakes in the past and try to find the pattern and then create forecasts similar to forecasts in weather. So for example, Floriana talked about how in the past, the average length of time between earthquakes on the Hayward Fault was about 150 years. And so that's about the range that we expect another earthquake to occur on the Hayward Fault. But we don't know. It could be as low as 130 years in between. We've passed that now. It could be as many as 190 years. And basically what we can do is take really fine measurements of how the ground is slowly inching along to figure out basically how much the fault hasn't moved. And then we can backtrack that to basically the debt that we need to pay in an earthquake. But when that's going to happen, what point of adding a little bit of stress is going to be too much stress for the fault to hold? We don't know when that is. And that's why some of our best tools are things like earthquake early warning, which is once the earthquake actually starts, we're going to very quickly start making things happen.
Thank you. That's sort of frightening. Is one, for my own edification, do other faults have different sort of average years? Like the Hayward Fault is 155.
Yeah, so the basically the stress debt that you accumulate is based on the much larger plate tectonics pattern. And so the rate at which the San Andreas like overall fault system, so the Hayward fault is sort of just like one splay off of a longer fault system. That's the Pacific plate and the North American plate moving past each other at about the rate that fingernails grow. And that means, but that stress is distributed differently on different faults. So the San Andreas fault has its own rate of accumulation. The Hayward fault has its own rate of accumulation. Going down to Southern California and you have the different splay faults, they all have their own different rates of accumulation. And there's also portions of the fault that are what we call freely slipping. So we don't expect earthquakes on those parts because as the plates apply stress, they're just moving. They don't have enough friction to hold them in place. Whereas we have points of friction on the faults that are locked that are causing they're trying to crank on it, but they're stuck at the faults. And then it's only when you've overwhelmed the force of that friction that they'll move, and they move quite suddenly as earthquakes.
Thank you. Here's another general earthquake related question, I think. Can we calculate the load on tectonic plates? Is there any technique to evaluate the plate gaps to predict the next move as per calculated load?
So as I mentioned, we can sort of calculate the stress depth that we have. So basically what this looks like in the landscape is you have the two big tectonic plates, and sort of at the center points of that, you actually do see like that motion happening, but it's not happening on the fault. So there's sort of this twisting action that's happening. But then when an earthquake happens, it's snapping the rubber band. So now the fault moves to catch up with what the outer reaches have already been doing. So we have a global network of basically high accuracy GPS sensors. So they know where they are, and then they're streaming back to satellites about where they've moved to. And using that, we can generate basically global scale tectonic maps of the rate of motion being imposed by tectonic plates. And then that will then generate how much we expect a fault to eventually move. What we do not know is if a fault is going to accomplish that motion, that depth that it has in one big go. Are we just going to have one massive earthquake, or are we going to accomplish it in chunks? So every earthquake that occurs is some amount of motion on that fault. The problem is that the really small earthquakes are exponentially smaller than the big earthquakes. And so they're just not taking up as much of that debt as we might like them to. But that's one of the challenges with prediction, is that we might be able to model what stress is going to be too much, but what we can't know is then how much is that going to go, right? Like there's a straw that breaks the camel's back, but like, is it rupturing the full length of the fault, or rupturing a quarter of the fault? Like we don't know how much is going to go until it's gone. So that's another big challenge with the physics, because we just don't have a clean enough picture of the fault all the way down to be able to model that properly.
Wow, the Earth is so fascinating. I like this depth model that you're just like the analogy. So here's another question, also related some way. What if two faults rupture at the same time, like the San Andreas fault and the Hayward fault? Would the force, would we find, if those two things happen, would we have a doubled or exponential effect on the ground, or do we know?
So this is, and Floriana can add on to this, but it's basically a math problem. And it's a concept of constructive or deconstructive interference. And so if you have the waves in the ground going like this, and if they're exactly aligned, they could cancel each other out, in which case where they interact, the ground will be moving less, or they could compound each other, and then the ground motion will be larger. The most likely scenario is that it'll be additive. There's just so much variety going on in the frequency content of the earthquakes that you'll just sort of have one on top of the other, as opposed to them sort of multiplying or dividing.
Yeah, I think, Sarina, you covered most of it. And,
Okay.
and I would just want to add one thing, which I think is very important, is that the probability that we have just concurrently the Hayward fault and the Santa Andreas fault just rupturing together is extremely low. We don't really just consider such scenarios. And whenever we design, we consider what we call the earthquakes that control the hazard at a specific site. So we know that there are sites in between the Santa Andreas fault and the Hayward fault, where both they can be just potentially hit by earthquakes from either fault, but really just we do not tend to not consider scenarios where the same structure is going to be hit by 2 earthquakes at the same time. So
That's great. I mean, that's not great. It's like, oh, I mean, I guess it's earthquakes are just the most amazing things. It makes me a little bit scared to live in the Bay Area, but also really excited to live in the Bay Area. There's one more question that just came in. Has any thought been given to artificially starting an earthquake while the potential impact is low, you know, sort of to encourage the earthquake fault to like pay off their debt a little bit? Is that even possible?
No.
yeah.
There's just too much that we don't understand or don't have a clear picture of deep underground. And playing God with that is just not advisable if you don't have a good idea of what's going on down there.
I mean,
Well, oh, sorry, we're gonna.
no, go ahead, please.
So I've got a couple questions for Floriana. The first is, you know, how do you anticipate advancements in technology that's influencing the field of earthquake engineering in the coming years? And actually, I guess this is the question for both of you since you're working in the technology space. But maybe we can start with Floriana.
Oh yeah, I can go first. Well, so certainly I think that just looking at the just path that the researchers like, you know, just the researchers working on this project are just defining, really just clearly there is a lot we can do by leveraging powerful computers, but also just models now, as said before, within EQSIM, they're able to really provide representation of these natural phenomena with this granularity, with this resolution. And so really just going back to what I was mentioning earlier, so I think that if now we all feel confident in just utilizing finite element codes to understand how our structures behave under earthquakes or under other, you know, just natural hazards, I think that there is clearly just a path forward to have, you know, the same type of building the same type of confidence with the ground motion simulation. So I think that moving forward, this can have just a large impact, an impact first at the just research community level as usual, and then just slowly just towards, you know, what we do in practice. So just and to really just then get to codes and standards. So I think that well, let me also add something. So we are utilizing the most powerful machine in the world, but we're not fully utilizing it yet. So just so there is still room to really just push this analysis even more. And if just a larger, just more powerful machine will arrive, so we will just work even more in that direction, including, for example, nonlinearities in our models and elements that we know are going to be computationally very challenging. But again, it's something that is becoming doable.
Thanks, Floriana. Sarina, did you want to add anything there?
Yeah, I think there's a lot of different nooks and crannies that we can sort of all expand on at the same time to advance this. So, you know, the expansion of networks like MyShake, or the development of the ways that we can use this data and the refinement of that really starts to open up some avenues for similar projects or similar types of analyses. The fact that there's just increasing amounts of data generally that we can start to build on and use as a backbone for this type of application. And then the other thing that's kind of neat is as we gain greater confidence in our models and our results, you can start to apply that in, for example, not just building codes, but building techniques. So if you have a better sense of the types of stress and motions that a building might have to anticipate, you can start developing more earthquake resistant technologies in the buildings that we build. Or if we are more confident about what we can expect out of an earthquake early warning system, you can start to develop technology to take steps automatically with that information. So, stopping elevators at the nearest floor so people can get stuck in them, designing alarm systems and critical technology for places like hospitals, having things that show up on signs when you're on a bridge or whatever it is. Like, we can start to, as we gain confidence in some of this technology, develop new technology to make use of it, and sort of spread out the effects and benefits that we can gain from it through that.
Got it. Thanks both. So Sarina, you mentioned bridges. Floriana, in your presentation, you had some images of things like pipelines. Does the research you're both doing, is that specifically meant to analyze only buildings, or can your research be extrapolated into looking at other parts of the built environment?
Okay, so no, actually the short answer is that any structural system can be analyzed. And so usually when we talk about just really buildings, depending on the extension of the spatial extension of the building, we just, are usually happy with the use of just one ground motion representative of that site, of the just footprint of that building. But, just having all these simulations becomes even more just compelling and just interesting when it comes to distributed systems, pipelines that you mentioned, but also like long span bridges. So we know that ground motions, and clear those maps show that, are not really just changing like linearly with distance, and really there is just high site-to-site variability, a strong site-to-site variability. And so actually, one of the one interesting application utilization of these ground motions with just distributed systems that we know can be potentially hit by ground motions that are different from site to site. Let's think about the Bay Bridge. We have just worked on the Bay Bridge, and so we cannot expect that all the piers will be hit by the same ground motion at the same time. There will be a time delay, and there will be also like a different frequency content from, depending on the site condition, from pier to pier. And so as a result, the behavior that we expect to see in the bridge, but again, even a pipeline, it's going to be strongly influenced by this site-to-site variability. And so really just in short, really the simulations at the regional scale are going to be able to inform the analysis and the study of a lot of systems, distributed systems as well as buildings.
Okay.
Floriana is exactly correct. MyShake, because it's phones that people have, and specifically we only record data when we're pretty sure that people aren't using their phones. That's what that half-hour wait time is for. We don't really expect to be able to make observations of, for example, like a bridge, because you're not usually just like setting your phone down on the sidewalk of a bridge and walking away for an hour, unless you've lost your phone.
Fair.
So MyShake in particular, we're focused on buildings because that's where our usership is. But there is a whole field of especially low-cost sensors and what you can do with them to monitor other types of infrastructure. So BART has looked into this to put it along with tracks. You can do this with bridges. You can sort of install them on the roofs of major critical pipeline type things. So there is also, like, Floriana's talking about the modeling space versus the empirical space. There are also efforts to see how efficiently we can get measurements of real things to inform empirical models.
Got it. Thank you. So I'm going to ask one more question, and I'm going to use host's rights to ask a question that I've been thinking about. So earthquakes happen all over the world. How specific is your research to the United States? What are researchers in, for example, Japan or Latin America, doing as it relates to earthquake research? Can you talk a little bit about the sort of international aspect of earthquake research?
Yeah. Sarina, do you want to go first, or want me to go
No,
first?
go ahead, Floriana.
Okay, so no, that's a great question. And the field of ground motion simulations and research in ground motion simulations is really active field of research all over the world. So we have just great groups in Japan, as you mentioned, great groups in Europe, and multiple groups actually in the United States. And it's probably natural that each group tends to focus on the area where they belong to. It's just something natural that comes with the knowledge knowledge and people that are just local people that have worked more just on, just that type of research from different perspectives. We need geophysicists, we need people with knowledge in geology, empirical models. And so we tend to see that each group tends to focus on, just a local, let me put it this way. Each group, they develop tools that can be just utilized, of course, for modeling any, just a domain anywhere in the world. But then each group tends to, just reproduce earthquakes and domains that are more like local. But given this, so each group is working on something well similar, but really just if we go into the details of these ground motions, the assumptions we make, and the type of motions we produce in terms of frequency resolution, and not only if they're deterministic or probabilistic, are different across the groups, which is great because each group is providing something different. However, at the end, really just what we, for example, the EQSIM is producing is really like a tool, an application. So whenever the EQSIM team will want to study an earthquake or just an active seismic zone in Japan, in Europe, or whatever in the world, they will be able to do that. It's just a matter of having knowledge about that domain, and really just that's it, and the default, of course. So I hope this answered your question.
Yeah, and with MyShake, it is a global seismic network. So we collect data from all over the world. And I showed an example of that hotel where we recorded a waveform and we measured the fundamental frequency. I've also done that with a building in Morocco, a building in Japan, just where we happen to collect data. However, because we're doing early warning on the West Coast of the US, that is where the majority of our users are. They're motivated to have the app for that reason. And that means that just the majority of our data comes from California earthquakes, where the earthquakes are happening. And in terms of some of the other things that I talked about, like, earthquake early warning, we are specifically keyed into the Shake alert system, which is US only. So I can't comment really on, for example, how fast alerts can go out in a place like Japan, because their communication infrastructure is different and we have no measurements of it. But they have their own app, and I'm sure that internally they have their own metrics of how well they're doing. And Google actually has a global network of doing this, where they leverage cell phones to detect earthquakes and then send out warnings to their users. It's just warning. It's like just a notification. And then you can basically Google the rest of the information if you want it. But they are basically, they've licensed MyShake technology to do this. And then put it out into the world on a global scale. So that's one of the ways in which we've sort of managed to translate that without necessarily having the resources to do it ourselves.
Got it. That's fascinating. Thanks both. Why don't I hand things over to Michelle?
All right, so we're at about our time. We all appreciate you guys coming and talking with us and sharing your research. It sounds, my take home from this is, one, I should get the MyShake app. Two, well, I have it, but I should tell other people to get it, which I'm doing right now. Two is that there is so much power in computing, from what's in your phone to supercomputers, to be able to protect us who live here in earthquake country. So thank you guys for the work that you guys are doing to help keep us safe and be able to help us in the future. I appreciate it very, very much. I am going to put up in the screen a QR code for a survey. So let us know, for you folks out there who are watching, how you think we're doing, and what we could be doing better, and what other things you want to be hearing about from our Midday Science Cafes. From the UC Berkeley sites at Cal, I want to say thank you. Jen, do you have anything else you want to say before we wrap up?
Yeah, just a bunch of thanks. Thanks so much to Floriana and Sarina for their great presentations, and thanks to our audience for asking excellent questions as usual. I'll just note that if you're interested in staying up to date on science coming out of either institution, you can go to science@cal.berkeley.edu, or you can go to lbl.gov and catch up on all the great things that our researchers are doing. So thanks so much, and we will see you next time. Bye, everyone.